Hi, and welcome to another video in a series to understand the atomic structure better. So today, in the last video, we said that we were going to look at harmonic oscillators. The reason for this was because we wanted to understand how we got an equation that looks something like this, for which is in fact the concept for a photon, where you treat light as a packet of energy. More formally known as a quanta. Alright, so today we're going to look a bit at blackbody radiation and what Planck did to sort of explain this better than previous physicists had. Now, to understand this, we need to understand what they were trying to do first. So, you know when you have a piece of metal and you heat it up, it starts, well, if you heat it up enough, like hold a knife over a gas stove or something like that, you'll see that it gets red hot. If you have burnt magnesium strips in chemistry labs, you've seen that they glow white. So there was a lot of time where people were interested in modeling the correlation between temperature and the maximum wavelength of emitted radiation. So temperature versus color with which it glows. Stuff glows. So why does it get red if you heat it, and then blue, for example, if you keep heating it more, or even white? Well, to understand this, they used a theoretical concept known as a blackbody, because a perfect blackbody doesn't really exist. So it's sort of like a thought experiment, like Schrodinger's cat, which is very interesting, so please do look it up. I will do a video on this further into quantum mechanics. Now, a blackbody is something that perfectly absorbs all radiation and perfectly emits it. So basically the only thing it doesn't do is really reflect. So a good example of something close to a blackbody is the sun, but in reality you don't really see a perfect blackbody anywhere. And a good way to model what a blackbody would look like is to think of a sphere with a small hole known as a pinhole, and you can have sort of like a triangular structure here. So any radiation you send in, radiation, word for light, electromagnetic radiation, right? It's just a wave. So you're sending in something, it goes through here, it bounces off, goes there, bounces off, goes there. So in essence, it gets trapped. So this would be a good example of something that perfectly absorbs everything. And we'll see how it perfectly emits soon. But yeah, this is a good model for a blackbody. So this whole thing with the whole pinhole where light goes in and doesn't really ever come out. But it will, but it's very unlikely that it will come out of this exact same path. Now, using the model for a blackbody, what they assumed theoretically was that, let's say you have a canister or square or something like that with a pinhole where you send in radiation and it doesn't come out really. So this thing can be modeled by using temperature rather than sending in radiation. So if you heat something up, it's going to radiate energy. Heating equals electromagnetic radiation. This is due to vibration of the charged particles, which we can look at later on. But you're going to have to take my word for it for now. So when you heat up a blackbody, like they assumed, they heat up the walls of the blackbody. Let's call this the inner walls. They heat it up and then it starts emitting, right? So far, so good. If you heat something, it emits, so this one starts emitting. And now because it's a perfect black body, it also absorbs it. So each of these walls also absorbs perfectly. So what's going to happen after a certain amount of time, let's draw a clock there, certain amount of time, you're going to see that it reaches what is known as an equilibrium, which means things are don't really appear to change with time. So they reach sort of like a stable state. And it's going to look something like this, because if it's always emitting, so always releasing energy and always absorbing energy, you'll expect it to reach some middle ground after some amount of time. And in this equilibrium condition, what a scientist, Rayleigh, assumed, which you can actually prove, is that you're going to see what are known as standing waves. Waves of electromagnetic radiation inside the cavity. So what this means is that, well, a simple example for this would be a guitar string. Let's say this is a guitar string that is plucked, so those are your fingers. You pluck it upwards, and then it starts vibrating. So it goes up and down, it sort of vibrates up and down. That is known as a standing wave. Something that's fixed on both sides and vibrates like that. You can have different ways it vibrates. So you can have something that vibrates like this, for example. Sort of like plucking it from 3 points, I guess. This is also a standing wave. And this is sort of a different, well, mode of vibration. Now, he said that the electromagnetic waves, once they go in and they strike the walls, they're going to set up sort of like standing waves. Standing waves, like in a guitar string, except it's electromagnetic. Alright? And this has to do because this wall acts as perfectly absorptive. So it sort of sets up like a zero and acts like the fixed points of a guitar string. So once you have these standing waves, what Rayleigh proposed is that the energy follows what is known as the equipartition theorem. Which is again another big word, but it's really straightforward. It's basically stating that the total kinetic energy, total energy of motion, is equally divided, equally partitioned amongst all available modes. So what is a mode? A mode can be, for example, moving in a straight line, vibrating, rotating, any of these. These are all modes. So all modes relate to frequency of vibration. So far, what he's saying is that given a certain temperature, you're going to distribute your energy across all these modes of vibration. That's one mode. There can be another mode which has a different frequency with which it vibrates, fast, slow, and all of this relates to the activation of electromagnetic waves, and the activation of a mode an oscillator gives rise to radiation. So an oscillator can be thought of as something like a spring. So a spring is an example of a harmonic oscillator because it goes left, right, and if you follow the path of a spring, you're gonna get a shape like this. So if this is the spring, right, goes up, and then it reaches a maximum point, And it starts coming down, reaches the lower point, goes up, maximum, lower, lower. And you get what is known as a sine wave. Now these oscillators have different frequencies. So what this guy is saying is that there's a correlation between temperature and frequency, and he explained it using the equipartition theorem. Now the problem with his explanation is that if you actually follow the final formula he gives out, you get a graph that looks something like that. For a given temperature, sort of energy density, wavelength. So he's saying that at lower wavelengths you're going to get a high energy density at a given temperature. Well, seems a bit complex, but essentially all it's saying is that if all oscillators, which are basically different frequencies, all oscillators, which are different frequencies, get activated to a different extent depending on temperature. Now, the easiest way to see what's wrong with this is to think about oscillators which have very low wavelengths. So those are X-rays, UV. There's a reason it's called the UV catastrophe. So if a UV oscillator is always activated, as he said, an oscillator corresponds to radiation of that type. You're always going to see radiation. That means this pen is going to emit UV radiation at all temperatures, which is kind of ridiculous. This is where Planck came in, and he modified this. He actually took a completely different approach. He looked at the molecules of the wall. And remember how I said that when they vibrate, they release radiation? So he said that these vibrations and he called these are again harmonic oscillators because they act like springs. He said that these vibrational energies are quantized, which means they have discrete values, which means they're not continuous. So you can have an energy here, you can have an energy here, but you don't have an energy in between. And they're activated when the energy exceeds the required energy, the energy of the oscillator. It said that you need sufficient energy in order to activate the harmonic oscillator, well, a mode of the harmonic oscillator. And this can be illustrated by looking at what this energy is. And he said that this energy is proportional to the frequency. It's given by h mu. So what he's saying is that given a frequency, you're gonna have sort of like energy gaps, where n is the natural number, ranging from 1 to 2 to 3, 4, so on and so forth, as levels. And only when the energy you give it in the form of temperature reaches a level, like a sufficiently high level, such as that one, only then will these two energy levels be activated. Now, what does the activation of an energy level mean in terms of this graph? Well, if you look at the experimental results for a given temperature that's sufficiently high but not too high, you're going to see a distribution that looks something like this, which might look familiar because it looks a bit like a Boltzmann distribution. And that's because Planck used a few concepts of statistical distribution of particles. So he used Boltzmann plus entropy. You can look this up and hopefully it'll make a little more sense. But microstates, to be specific. So essentially, if for a given frequency that's sufficiently high, let's say uv, which has a high frequency, the gap between the first level and the second level is going to be very, very high. And it's never really going to get activated. So the number of atoms or molecules that actually show this sort of activation is really low. So you're going to get a distribution that looks something like this. And this is where you're going to see the peak sort of filling up of these energy levels. So by sort of distributing energy over discrete quantized vibrational energy levels, he successfully explained why we don't see a lot of UV radiation at very low temperatures for random substances like my pen, for example. Explained Blackbody radiation. Now this step to sort of discretizing, making something continuous discrete, was actually a step forward towards the development of future theories in quantum mechanics. And that is why I decided to do this video on sort of like harmonic oscillators, Planck, Blackbody radiation, because it leads up to everything we know about quantum mechanics. And I hope this serves as an interesting introduction to what you will learn in greater depth in upcoming videos.